So what's the difference between composite and base radar? Again, a very common question I get. Well, the NEXRADs basically scan the atmosphere using 360-degree sweeps, multiple sweeps around from elevations as low as negative 0.2 degrees all the way up to 19.5 degrees. We call that a volume scan through all those. And we know the radar, it's a forward-pointing pencil beam radar. It sends out a pulse of energy, and that strikes various airborne objects. Typically, those that are associated with weather are called hydrometeors, like raindrops or snowflakes, hailstones, ice pellets. And the radar then listens for that backscatter radiation, and they measure that in the reflectivity parameter of Z, and it's usually recorded as decibels of Z or dBz. And at your next hangar party, you can put out some trivia out there and say in 1 hour, the radar is on for about 7 total seconds, but it's doing an incredible amount of listening for 59 minutes and 53 seconds. So the radar is really doing more listening than it is sending out a signal. And so every elevation scan from the lowest all the way up to the highest all produces what's called a base reflectivity product. So you may have been taught when you say, hey, I want to look at base reflectivity, you think it's lowest. The term base does not mean lowest in this particular case. That's because every elevation scan has base data associated with it, whether it's reflectivity data, velocity data, or what's called spectrum width. All these have base data associated with it. It turns out that most of the ones that you look at, either on the internet or on your favorite heavyweight app, they usually show the lowest elevation, and they usually call that base reflectivity. They really should call it lowest elevation angle or lowest tilt, to be clear. So again, 2 reflectivity products we generally look at here. One is called composite reflectivity, which is essentially the maximum in a column of air. So you start at the surface and go all the way up to the top, and whatever the maximum reflectivity value is from all elevation scans in that volume, using all the possible elevations, that's the reflectivity that's used. So it's the worst case scenario, if you will. Whereas base reflectivity from the lowest elevation scan, the lowest tilt, is usually kind of representative of what's falling out of the base of the cloud, because that's the lowest scan that the radar sees. And so when you're looking at composite reflectivity versus the lowest elevation angle, what you generally see is that the composite has a much larger footprint to it. Essentially, what's happening here off the coast of Florida is that in this particular case, the composite actually will see some of the ice crystals that are in the storm's anvil. We see that fairly frequently. Sometimes not necessarily useful to us. We're not flying up high. If we're flying down low, we really don't care what's out there. But you should always, in many cases, be looking at both. So I always tell folks that typically when you're looking at the base reflectivity, the lowest elevation, that usually represents a really good, it kind of matches pretty well with what you see outside the cockpit. So you can see where the individual cells are. So flying in this particular region where you see those higher ice crystals in the anvil probably is not going to be a problem for you to fly in that region overall. But also you have to look up here where you see there's an area where the base, and then you see the composite, where you actually see what appears to be that the precipitation core is elevated. So the radar itself is essentially at the lowest elevation, is not seeing that. It's seeing what's happening higher up. So in those particular cases, it's always best to kind of be looking at both of these, but the base is going to be more representative. Again, it's going to meet the sight picture, which you see outside the cockpit, especially when you're flying down low.